Metrics. As engineers, as builders, we love metrics. We love to measure things. We measure how many transactions per second, latency to microseconds, how many times we've deployed in the last minute, hour, and day. And the reason we like metrics is because it makes our results visible. So when we built this presentation, we thought hard about what your metrics may be for reInvent. Would it be to obtain 1, 2, 3 ideas that would impact your organization positively by 20, 30, 80%? So in the next 60 minutes, the 2 presenters here will step you through the experience that they gained in building 2 platforms that jointly process more than 1 trillion transactions per day to present you with 24 golden nuggets, those ideas that you can actually take home. So it's my pleasure to introduce Viktor Gershkovich, team lead for AppsFlyer, and Akhil Andapali, senior architect for advertising and marketing at AWS. My name is Jerry Lowe. I have the privilege to lead the technology team for advertising and marketing at AWS. Victor, take us away.
Thank you, Jerry. Hello, everybody, and thank you for coming. Hope you are having a wonderful day and ready for some interesting content. When I thought what would be a good way to start this talk with, this picture popped right away. As engineers, we're always trying to meet demand, make things work, be stable, and deliver results, just like this awesome bartender. And it works great when you have a couple of dozens microservices, few centralized databases, and more or less persistent traffic you can expect. And then this happens. And dozens become hundreds. Your centralized databases are up to its limits, and traffic grows by days. And this is a whole new festival. You must optimize, be efficient, adapt, and innovate to handle the scale. My name is Victor. I'm working at AppsFlyer for the past 4 years, managing the real-time infra team, responsible for the distributed event streaming technologies, cache engines, and key-value databases. I have more than 10 years of experience at the AWS ecosystem, love working at scale, and a big fan of a good night's sleep, without any on-call interruptions. If I could have told you that in 6 months, you can improve your infra with latest technology stack, boost performance, and get a massive cost reduction, would you believe me? Who thinks it's possible? Well, this agenda will tell you my story. We will talk about AppsFlyer and our message-driven architecture. I will share our journey from a classic EC2 approach to EKS infra. I will share our usage of Graviton optimized storage instances and how it improves our infrastructure from cost and performance perspective. And finally, I will show the service level we were able to achieve for our developers using this new architecture. Let's start with a short intro of AppsFlyer. AppsFlyer is the world's leading mobile and measurement attribution platform. We're backed by the leading VCs in the world with more than 1,500 employees across 90 offices globally and with over 65% in mobile market share. Our objective is to do everything in our power to help our customers optimize their app growth and user acquisition efforts. Data is the core of our product. Our customers can measure user activities across multiple platforms. This gives us the ability to expose detailed analytics and help them make the right decision on where to focus their campaign efforts. This is how our real-time event count looks like on a daily basis. Our ingress and internal service communication generates around 800 billion events per day. At peak hour, we go above 12 million per second. Specific days or week, we might instantly grow by 10, 20, or even 100%, depending on special events like sport events, or sales days like Black Friday, which is still currently running. To support it, we have over 400 engineers running more than 1,000 microservices spread across 2,500 thousands of cloud resources and dozens of third-party integration. In our real-time flow, we run over 60 different Kafka clusters, which holds more than 1,000 brokers and handles around 800 terabytes of data at any given time. On average, we support 65 production deployments per day. Now that you know who we are and what we do, let's talk about how we do it. Before we jump into EKS architecture, let's talk a bit about the conventional way of running stateful databases. To simplify, we're usually running on a single AWS account, main region and VPC, private subnets spread across multiple availability zones, right? This is being managed by infrastructure as code, configuration management tools, DNS and service discovery, CI/CD pipeline, secret management, observability stack, and other open source or internal tools to support the scale, management, and close visibility gaps. Familiar, right? Overall, it has a lot of moving parts and complexity when handling high scale. Day-to-day operations become much more complex and time-consuming. It is difficult to introduce new features and capabilities, and eventually, unfortunately, you find yourself maintaining and not developing. This is why we decided to make a stop and move to EKS. I was asked frequently, why EKS for stateful database? Why not just to improve and invest in our current architecture, as running stateful application over Kubernetes might be a bit challenging, right? Those are the reasons. We wanted to decrease the tooling, overall management, and centralize our ecosystem. EKS gives us the ability to do so with all the needed elements to run and control the Kubernetes cluster and use its services. We can easily deploy our application, control its lifecycle, and develop controllers and operators which fits our needs. This has a direct impact on our velocity and the ability to move fast, adapt new features, application, version upgrades, and develop new capabilities. As we switch to a pod as our smallest deploy unit, we can easily adapt new instance type and take the benefits of the AMI and kernel versions, which can boost performance, stability, and reduce security risks. And of course, we wanted to increase our efficiency in resource management and cost optimization, which is one of the core benefits of Kubernetes. In addition, working with EKS allows us to make full adoption of infrastructure as code and implement GitOps flows all around. Everything is visible in code. We can implement self-serve approach and give our developers the power to commit and safely work with our infrastructure. And finally, we enjoy the full power of the community. We can easily deploy and control open source projects with minimal effort. Now that we talk about what we are doing and why we wanted to make a change, let me show you how we implemented it. Let's start with the high overview of the architecture we chose. We run EKS per Kafka cluster, which is bound to a business logic. Now, it might be a bit confusing and unconventional as there is a small overhead of resources, but remember, Kafka is the heart of our system, with over 1,000 microservices using it every single day. By making this decision, we avoid multi-tenant approach and have full ownership of the EKS cluster and the running application. We are fully independent. We also reduce a single point of failure. In case of any issue, only one business flow will be impacted, and we can focus on its recovery. In addition, we can make surgical operation to the EKS and the running application with low and calculated risk. And of course, we can tune for best cost performance, as every business logic has its own needs and trade-offs. This made it possible to deploy it easily in multi-account and regions, and have full separation between production, staging, and development environments. Full deployment takes around 30 minutes, fully automatic, and can scale up and down by demand. We run on main VPC with private subnets spread across multiple availability zones. This way we have resiliency. And we enjoy multi-AZ traffic reduction as we implemented rec-aware and our microservices reads data from their specific AZ. We are running on 3 main node groups, 2 stateful for Kafka and Zookeeper, which are currently coupled. There we run pod per node full resource allocation, and we can easily scale up when adapted to the auto-scaling group. We run stateless node group for all the utility and complementary services, such as UI tools, metric exporters, and other stateless applications that support the Kafka management. There we are running on spots, which automatically scales up and down by resource use. We chose to use Route 53 as our main DNS and service discovery. And of course, elastic load balancers were needed. This enables a simple implementation for our external client connectivity. Now, this architecture allows us to have full control of our ecosystem and supply it as a product for our developers. Just to illustrate, think about this picture for a second. Everything is in one place, very optimal, has all the needed tools, and ready to be used anywhere at any time. Let's talk a bit about the internals, and I would like to focus on 3 main areas, which I believe are the most important to get you started, and you will definitely face when running your stateful databases over EKS. Those areas are the way you manage your nodes, working with storage, and of course, the network implementation. Let's start with the fundamentals. EKS gives you the option to work with managed and self-managed nodes. Let's see the difference. Managed nodes are great for stateless application. Their lifecycle and updates are being fully controlled by EKS. Node updates and termination automatically drain nodes to ensure that your application stays available. And basically, you have nothing to worry about besides your pods. Self-managed nodes, to the contrary, are better to run stateful applications, as we want full control of the node lifecycle. Without it, we might lose state and data. We want to make sure our application is stable and has data persistent before making any modification to the node. And of course, we can control the operation system, AMI, and kernel parameters, which can boost your performance. We chose self-managed for Kafka as our stateful application, and managed for our stateless utility group, and enjoy the benefit of each option. Now let's talk about storage. And in our case, the local instance store. We chose it due to high performance, storage capacity, and low I/O latency. This helps us cover our entire R&D and production requirements. Let's see how it works. We integrated an open source tool called Local Path Provisioner, which creates the physical volume from the node mount. It gets a full static allocation for the volume and controls the mapping to the persistent volume claim created by the pod. Local storage has the performance benefits. However, it has one major limitation. In case of node failure, we must be able to automatically recreate the bound to the persistent volume claim on the new physical volume. We solve it with the Kubernetes jobs that checks pod in pending state, finds their physical volume, checks if the node is still alive, and if not, delete the persistent volume claim and the physical volume, which are no longer in use. At this stage, the pod will create a new claim and will bound it to the new physical volume on the new node that will be created after the failure. This way, we get high disk performance, fast self-healing capabilities if node fails, and replicate and write our data as fast as possible, and of course, enjoy the high storage capacity. Networking. Networking is always a concern. We all battle latency, discovery, and DNS issues, which might surprise us from time to time, right? Let me show you how we implemented the networking. In our case, we chose to work with node ports for low latency combined with discovery stability to reduce DNS cache issues for producers and consumers. A node port is a special type of Kubernetes service. When created, Kubernetes will allocate a port on all nodes of the Kubernetes cluster and will make sure that all the traffic to this port is routed to the service and eventually to the pod behind that service. This way, first broker discovery is being done to a DNS record in Route 53, which holds all the nodes in the cluster. This first discovery redirects to one of the Kafka nodes, which sends the list of all other brokers with specific port mapping using Kafka Discovery Protocol. Once received, the clients work directly with the broker node DNS and the port allocated to that broker by its number. This gave us low produce and consume latency as traffic flows directly to the dedicated broker and remove any network interruption or DNS cache issues if pod fails or restart, as node IP does not change and pod IP allocation does not play a part in the discovery. This ends our review of the journey we took from a classic EC2 approach to EKS, its benefits, architecture, and a few areas which were fundamental for the implementation. Now I would like to explain why we chose to use Graviton storage optimized instances. This AWS blog post was written 1 year ago, introducing first storage optimized instance with Graviton 2 for high throughput and low latency access to large amount of data over the local storage. This was a great match for us, as we mainly use i3 series and constantly battle between compute and storage. Working with EKS removed our dependencies for node configuration, and we can start using those instances. Let's talk about the benefits. We get maximum resource efficiency as we work with Nitro-based system, which gives high hardware performance, close to bare metal. And of course, enjoy the new CPU architecture, which is very optimal for our workloads. Flexibility and choice. This has a very good balance between CPU and storage. We can adapt our cluster to a specific use case and get the maximum benefits of the needed resources. And finally, we enjoy high performance for storage and networking, which goes up to 30 terabyte and 100 gigabyte per node, which results in low, high latency, high bandwidth, and storage capacity. Let me show you a few examples. This is one of our production clusters, handling a peak of 3,500,000 requests per second. Message payload is around 1.8 kilobyte. In this case, we were able to reduce the node number from 27 to 6. Improve produce latency by over 90%. Reduce consume average time by more than 30%. And reduce CPU consumption by 16%. Cool, right? Let me show you one more number. The cherry on top, and the number our managers always like to see, we reduced cost by 60%. Now, this has a perfect package. We improved performance, reduced cost, and did not harm any offering for our customers. We only improved it. Let's talk about flexibility. In most cases, we always need to trade between CPU and storage. Sometimes networking is also a factor. In the left, you see a spreadsheet of well-balanced clusters that were migrated from i3 series, each using different instance type based on needed trade-off. We can see that the cost reduction is between 47 to 72%, an average of 65%. This was possible due to really good balance between the CPU and storage. So when CPU is more intensive, we can use the IM instances. And when storage is more important, we can use the IS. In both cases, the CPU and storage performance are the same, just the size matters. And networking starts with up to 10 gigabit, up to 25 gigabit, contrary to the i3 that started with up to 10. In addition, the cost is well balanced as well to support those needs, as the difference between the two instance types shown here as an example is only 40%. So you get double the storage, same CPU, but pay only additional 40%. Let's talk about performance. This is an example of a cluster that holds 9 nodes, which handles 1 million events per second, with around 125 gigabyte of incoming traffic. It has a storage of almost 30 tera. The producers write a message size of around 1.4 kilobyte with under 50 millisecond latency. Consumers fetch twice as the incoming traffic. Now again, one of the benefits is that we can add more consumers to this cluster and utilize the high bandwidth, which starts with up to 25 gigabit per node. CPU is perfectly utilized and stable around 75%. This is a number we all love to see when running our infra, right? As it means we are perfectly utilizing it. It also means we can suffer a node down and still handle the scale and recover it on our convenience. Up until now, we talk about Graviton-based instances and the migration we did from classic EC2 to EKS. Now I want to show you how we combined it and gave our developers a full self-serve package to work with in our infra. Meet Daniel. Daniel just started working at AppsLayer a few months ago as a backend developer. He's very productive and writing a new feature that needs Kafka cluster to write and consume from. He's probably thinking about who should he contact, how long should he take, what resources, configuration, or information should he provide, and what happens if we want to add more topics or configurations in the future, or even scale up the cluster. And this is where we come to play. We provide a single API using Terraform with an open source tool we wrote called TerraCrust, which enables Daniel a simple user experience and hide system complexity. Feel free to scan the code. It will redirect you to our repo, and I'm sure you will enjoy its content. This is the basic configuration. As you can see, the developer provides a basic metadata about their service, and the cluster is being created with default values behind the scenes. The developer can always override depending on his needs and level of expertise. And all the options are visible in a detailed documentation we provide. You can see topic lists and its configurations, broker number, and other utility services like Mirror Maker. The complexity of AWS account, services, third-party integration, and even the application running are not exposed. But again, its configuration can be changed if needed by the developer at any given time. We, of course, have validations and enforce policies to make sure we protect our infra and protect the developer from doing mistakes. Once the change is committed, we have a GitOps flow, which apply the state and push to production. So if Daniel wants to change or create topic configuration, or even scale up the cluster, he's only one commit away from doing so. Just to give you a high overview of the flow. Everything is being managed in source code. in the file you just saw, which sits in the developer's repo. We expose our infra and application deployment with Terracrust, which enables a simple API to Terraform modules we develop and control. The lifecycle is being managed and run by Flux, which monitors Git events to our Terraform files on all repos and trigger and apply after validation and policy enforcement using an open source engine called OPA. To seal the state, Firefly listens to state change based on AWS events and can trigger and apply to the source code and overwrite any manual changes. This ensures we do not have any drifts from the source code. This entire flow gives us the ability to control and expose our entire infrastructure, starting with AWS resources, up to the application running on Kubernetes, and extends to third-party integrations like Datadog and PagerDuty. All from a single state file, which sits in the developer repo. So Daniel just created all the AWS resources, such as the EKS cluster, Route 53 records, load balancers, and many, many more. Deployed Kafka, operators, and utility applications to Kubernetes, and created dashboards and alerts to his specific team. All that is being managed in source code with full visibility and control. This concludes our agenda. We talked about AppsFlyer, our transition from EC2 to EKS, the usage of Graviton instance type, and how we empower our developers. At this point, I would like to show you one more slide that summarizes the value we got. We see around 30 to 90% decrease in latency. Operations such as provisions, version upgrades, configuration management, and many more went from weeks to days or even hours, and in many cases were forwarded to the developers. And up until now, we see around 65% decrease in cost reduction, which is huge for our yearly budget. Thank you for spending the time with me. If you have any follow-up questions, feel free to send me an email or LinkedIn me. Thank you, guys.
So I think the way we vote these days is like this. So I think that was a very high vote. Victor, thank you very much. Awesome presentation, journey. I especially like the outcomes, was incredible. So I look forward to see one of you next year on stage here telling your story and your results. If you have such a story, please do email us. Show of hands, who is in programmatic or knows what programmatic advertising is? Okay. So there are 4 factors that really make programmatic advertising a fun environment to actually work in. The first one, is volume. You heard about trillions of transactions per day. The second one is that you have to process this in single-digit latency, below 20 milliseconds, most frequently below 2 milliseconds. The third one is that you have to do this very cost efficiently, right? Like really, really cost effective. And then the fourth one is these volumes change dramatically, very rapidly and quickly. So in the next 20 minutes or so, we're going to show you 12 gold nuggets of lessons that we've actually learned in building a real-time bidding platform on AWS. So just a quick overview. In the 500 milliseconds before an ad is displayed on your device, that device issues a request to an ad exchange, number one. The ad exchange actually launches an auction and send that request to all interested buyers, the DSPs or demand-side platforms. That buyer evaluates and determines how much they're willing to pay for that request and respond with that request. The ad exchange evaluates that and picks the winning request. and then send that winning request back to the device. The device then used that request to retrieve the actual creative, number 4, get add, and display that creative. And then subsequently emit the number of beacons to actually indicate that it received the creative, that it displayed it, that it was viewed, maybe that it was clicked on. Now, as you can see, one add request results in about 42 different requests or transactions, right? And this happens 1 to 2 to 15 million times per second. And that's where these billions or trillions of transactions come from. And this is just for one participant. Now, this happens at all the DSPs, all the ad exchanges, and for the publishers. So let's step through a few best practices that we've actually learned. The first one is, quite frequently, we deal with a stateful architecture or a legacy architecture. Nothing wrong with it. There are many cases where this is a good architecture. So in a stateful architecture, your state is maintained in memory. You capture your logs on local disk, and then a batch job periodically will actually write that log file to a data lake, and you'll periodically update the state in memory. Right. The challenges with that are that it takes time to actually hydrate the state, and it takes time to actually drain that instance when you want to terminate it. Now, in the cloud, you don't always get a nice notification to actually say it's going to be terminated. It may just die, so you'll lose data. So the first recommendation is take the time to actually migrate your architecture to a stateless architecture, and we recommend doing that in 3 steps. The first one is to actually migrate your state to a data store. And in this case, something like a NoSQL database. We see DynamoDB and Aerospike very frequently in that space that can deal with billions of transactions or records and millions of transactions per second in like less than 2 milliseconds. Not a trivial exercise, but really worthwhile doing. The second step is to actually separate your processor from your data producer. Right? So that data producer will actually write your data into a data stream like Kafka or Kinesis, and we'll talk about that in a little bit. And then the third step is to actually persist that data stream then into your data lake. And what this will enable you then to do is to actually use auto-scaling so that you can increase and decrease your infrastructure size at will and very quickly. And we'll get to how that further impacts your architecture. So Akhil.
Yes. Let me start with a question. How many of you use Spot instances? How many of you use 100% Spot instances for your real-time bidding? Awesome. So the next 4 things are few best practices that actually help customers to aggressively use Spot, like 80 to 100% on Spot. Number 1 is to minimize your boot time. So minimizing your boot time will help you. Let me start with what Spot is. So EC2 Spot is extra capacity that is available in EC2 fleet that you can get for a 90% discount, up to 90% discount. But you will also have this 2-minute notification when the instance would be terminated. So you have just 2 minutes to reboot a new instance and replace that instance. So you need to minimize your boot time. So by adding all the dependencies and libraries pre-installed into an AMI, so that you can replace that instance within 2 minutes. The second best practice is to go with attribute-based instance selection instead of using static instances from a particular size or a particular instance family. You can set up your Spot auto-scaling group by enabling attribute-based instance selection so that now you can go across multiple instance families with number of CPUs, memory, or network throughput that your application needs to run. So this will help you to go across instance families and find that Spot fleet to replace the instance. Third one is to enable capacity rebalancing feature on your Spot auto-scaling groups so that you would get the termination notification well in advance to that 2-minute notification. We have seen customers getting it up to 10 minutes before the 2-minute interruption notification. And the fourth one is a proactive tip to actually keep monitoring the Spot placement score. This is a score from 0 to 10. 10 being the highest number of instances available in a particular instance family, and 0 being there are no Spot instances available in that particular instance size or family. So you can keep monitoring the Spot fleet in the AZ or region that you're working with so that you can proactively select the Spot instances based on that. And we have seen customers going from 80 to 100% utilization on Spot, and they were able to save across 60 to 80% in cost by moving to Spot.
Thank you, Akhil. So, show of hands, how many of you are using Graviton today in production? Okay. So, my number one recommendation in all of reInvent this year and last year and next year is to go back and try Graviton immediately. Here is why. So, Graviton 2 provides up to 40% better price performance over similar size x86 instances. And we're going to show you, this is not just talk, this is in reality. Add to that the additional 25% cost performance increase Graviton 3 provides over Graviton 2, and you're talking some real numbers now. Now, there's a third reason, not on the slide here, that I personally really like. So Graviton 3 consumes 60% less energy than similar-sized EC2 instances, right? So for those of you that actually have a sustainability target or want to impact your carbon consumption, this is really a great reason to actually migrate to Graviton. So I really, really recommend that. Now, you may think that it's difficult. My God, it will take months. On average, customers see that it takes less than 2 weeks. And the majority of the workloads, as you can see here, is actually relatively easy. Now, should you run into a package or a library that is not available on Graviton, we have a Graviton-ready program. So let us know. And that's a program to assist those partners then to actually migrate their package or their library to Graviton. Now, we highly recommend that you go to this site, getting started with Graviton. It has in-depth information to help you along your journey. And there's a really good tool in that, right? So the Graviton Performance Benchmark. So once you've migrated your app, you run this benchmark, and it will help identify areas that you can actually improve. So we highly recommend this. Remember we said 40%? So these are real customers, and the results that they've achieved. You just heard from AppsFlyer what they have achieved. Now, of course, numbers will depend on the specific workload. But by and large, we actually see customers achieve well above the 40% that we actually promise. So we did 3 things, right? We went from Stateful to Stateless, then we went to Spot instances, and then we went to Graviton. So let's actually see what's the result of that. So we start off with an application that's Stateful at $100. We move it to Stateless, and we implement auto-scaling, and now we only pay for what we use. Then we went to Spot instances, and then a conservative number for Graviton. And you can see you've reduced your workload now by 84%. Right? So I hope this provides the numbers that you can use to justify or to prioritize your workload and the time that it will actually take to really take these steps. They're not hard. I highly recommend that you actually do that. So remember, we talked about separating your processor and your data producer. So if you use Kinesis, the 2 tips here is simply this. Kinesis has a payload unit size of 25K. So the first tip is combine your records so that it actually optimizes that size. So if you have a record size of 1K, combine 25 records and put it into one put to make it 25K. The second one is you don't have to write every payload size, right? So you can combine 100 of them and then just write one record because you get charged for every time you do a put. And those 2 things can really, really significantly reduce your Kinesis cost. Now, Aerospike, we love Aerospike. Yes, yay. So a few things in terms of Aerospike. The first one is configure your Aerospike cluster to be rack aware, right? And then configure your application to use that rack-aware feature. And what that basically does, it will actually send the request to the specific data set in the same AZ, right? And that avoids cross-AZ data transfer cost, which will actually add up pretty significantly. The second one is, the workhorse for Aerospike clusters is typically i3N instances. And so we have customers that actually experimented with the i4I instance, and they achieved 23% cost reduction just by moving that. Now, the big news for me of this quarter is on November 15th, Aerospike actually announced that they are now running on Graviton, right? Raise of hands, who has heard about that? Okay, just the Graviton. So this is really significant. Here is why. 63% cost performance reduction running Aerospike on Graviton versus similar-sized x86 clusters, 63%. So I highly recommend that you go and try out Graviton for your regular workloads and then try Graviton for your Aerospike workload. So reducing data transfer costs. Back to you, Akhil.
Thanks, Avi. I love this topic. I love talking about data transfer costs to ad tech customers. According to me, the best way to save money on data transfer is to not spend it. How you can do it is by creating an ML or AI model, which kind of predicts if the bid request is going to return a bid response. And if you take the average, 90% of the bid requests that are sent are receive no bid responses. So why to send it if you know if you can predict if it's going to be a bid or no bid response, right? So build that model and use that. So if you have not yet using that, we have developed an open source ad intelligence kit, which is available on AWS GitHub. So please check it out. And second thing is private link. How many of you use private link? Awesome. So use private link to connect to your partners on same AWS region. This will help you reduce data transfer cost. We have done a small POC with a couple of partners, ad tech partners on AWS, where the DSP or demand side partner were able to save 95% in the cost, and SSP or supply side platform have seen 15% uplift in revenue. So they have seen significant uplift in revenue as well as data transfer cost savings. If you want to learn more about private link or POC that we have done or what's coming next on that, we will be available at the AMT Lounge in Caesars Forum. So please stop by and we can give you more details. And the third one is not an architecture or design best practice, but it's more of a cost best practice, where we have seen customers confining their entire infrastructure into one AZ, but having that deployment scripts ready to fire the entire infrastructure in a different AZ or region when the primary AZ goes down.
So up to now, we talked about kind of infrastructure, architecture changes that you can make. So now in the next few slides, we're going to really talk about software application changes that we can actually make.
Thanks, Jerry. So with all these best practices that we discussed, we went to work. We took the OpenRTB 2.0 framework, and we started building a real-time bidding application on AWS. So we implemented all the best practices that we said, but we were not able to see the results. And the first iteration, we have processed 7,000 bid requests with a latency of 30 milliseconds. That would not even be close to acceptable in ad tech ecosystem, right? So we started iterating the code, and we realized that we have done premature optimization on the infrastructure rather than optimizing the code itself. So here are a few things that we have done to optimize the code. So first thing is improving the scalability on the web server. The scalability on a web server, the bottleneck is actually one socket listener actually listening to all the incoming requests and passing on to the workers. So the workers are sitting idle until the request comes in. So we want to eliminate that. So how we did that was by enabling so reuse port on our Nginx web server. So by enabling so reuse port, it will create a socket listener for each individual worker listening on same IP and port. So this actually improved our Nginx performance by 4x. So when we saw this, we started to see, we wanted to know what are the hotspots on our code itself. So we did performance analysis on our Linux instances as well as the code. Used flame graphs to identify the hotspots. And the next are a few things that we did to optimize the code. So the second one is Jerry.
Okay. So just a show of hands, how many of you are actually using something like a flame graph today to identify the performance of specific components, either CPU or latency? Okay. Highly recommend it. Google it, flame graph. So what we did here is logic says if I run one instance, one container consuming all 64 or all the resources available, that would be best. Interestingly enough, that's not true. So we experimented with different configurations. In this case, you can see we ended up with 32 containers or bidders on one instance. And you can see, that's roughly 3x improvement in throughput and a reduction in latency. So experiment with the number of containers per instance.
Cool. Oops. So the next hotspot that we found was the JSON standard library that comes with the Go package, right? So whenever an incoming request comes in, it's basically a JSON record that's coming in. And the Go has to allocate memory to read that data JSON file, create a structure, data struct, create schema, and then read the data from that schema. So that was taking a lot of CPU and memory. So what we did was we replaced that JSON library with FastJSON library, which actually can read JSON file without actually creating any code or schema with value.get function in it. So this helped us to lower our latency by 50%, and we were able to process 25% more bits at a given point of time. So the next thing, or the next hotspot that we found was with the the standard HTTP library that comes with Go again. So the standard HTTP library, as soon as the request comes in, it will create a Go routine, and then the Go routine will be allocated a memory, and then it would send into a pool where processor has to come and pick up the request, and this is like a lot of process. So with fastHTTP, what happens is with the server and handle method in that, you can directly, as soon as the request comes in, you can send it to the processor for processing. So this actually reduced the latency a lot. It reduced the latency by 90%, and we were able to process like 15% more bits by replacing the library with fastHTTP. But one caveat there is if you want to replace your net HTTP or standard HTTP library, fastHTTP is not that drop-in alternative for standard HTTP. If there is any framework that is using net HTTP library, then you might have to consider moving to fastHTTP. And fastHTTP doesn't support HTTP2, so that's another drawback.
Okay, so the next tip is one about a logical construct in your architecture. So as you can see here, in the first one, you would parse a request, you would retrieve the data, you would construct your response, then you would write that into your data stream, and then you would send your response. Right? Now, writing that request takes 5 milliseconds. So simply by making it a non-blocking task, you would actually send the response before you actually write to your data stream. You reduced your latency by 5 milliseconds. Now, a couple of things to remember when you do that is, as you can see at the bottom here, you have to make sure that writing your data takes less time than it actually takes to process it. Otherwise, you'll have a growing queue. Second thing is you actually have to monitor that queue so that you can take action if for one or other reason that queue writing your data away is actually increasing. So just a logical construct, look at what is actually blocking and what you can actually move into a parallel path or a secondary path.
So the last thing, so our application was performing in an optimized state now. So our data stream is what we have to optimize now. So we use ZStandard compression. It's an open source compression program with a better data compression ratios. So we use this to compress the logs and transactions before handing it over to our Kinesis producer to aggregate. And by doing this, we were able to aggregate more records in a single put payload, which is 25 KB. And the Kinesis producer latency has decreased by 90%. results.
So what would you imagine? So we looked at 6 steps here, right? And as you see, we actually didn't really change code. In one place, we actually moved the logical order. So let's actually look at what the results were. So you can see here that we were able to increase the throughput by 21x, right? And more importantly, the latency by 29x. 6 steps, simple to do, right? So key here is, go and try these, use flame graph, identify what is your biggest latency, your biggest CPU producer. So with that, I'm really delighted to say, first of all, you can go to the AWS Solutions Library under Advertising and Marketing, and you can actually find the solution guidance for this bidder that we actually spoke about here. And in about 2 weeks, that will include a link to an open source library where you can actually get the code that we actually created for this bidder. So we're looking forward to actually hear your feedback on this. So with that, we come to the end.
We have 8 minutes, so we'll open up for questions.
But I do want to say one thing, 2 things, really. So first of all, thank you for taking the long track out here to join us today. Number one, it's much appreciated. Second one is we learn from your feedback, right? So if you actually like this, please go to the app and give us a high score. That enables us to come back. If you didn't like it, we would like to get your comments so that we can improve for the next time. So with that, I just really want to say thank you again to Victor and to Akhil.